Well, thank you, Charlie, and thank you everybody for tuning in. I'm going to do something which is going to be quite difficult and talk about a subject as vast as volcanoes in 20 minutes, and then take some questions. I want to focus really on the areas that I'm personally interested in volcanic geology. That involves three areas really, if I break it down. Place, so that means where do these volcanoes take place, where do they occur, and why? And that involves the more traditional aspects of geology. So a lot of that is around field work and observations, observational science. If that's what you're interested in, then that's good. I'll touch on that. Then I'll say something briefly about people. People are really important in volcanoes because volcanoes are hazards and they kill people every year. So how do geologists and others go about mitigating the hazards of volcanic eruptions? That's another whole area it takes us into disaster management. And if you're interested in engineering or economics or aspects of sociology, then volcanoes play a role in that. And finally, I'll take us out of the Earth, out of the inner solar system, out to the outer planets, Jupiter, and out to Pluto. And we'll look at extraterrestrial volcanoes. And if that's your thing that you're interested in, then that ties in nicely with astronomy and physics. So what I want to try and get across is the idea that volcanology isn't just about geology. It covers a whole range of different disciplines that you might be interested in. And you can make a contribution in any of those areas. They're all rich for research and they're great learning experiences, no matter where you end up going to university. Right then, so let's start at the beginning with place. I'm going to show this video. There's no sound. I can hear the sound on it, but on PowerPoint over Zoom, I don't think you'll be able to. In 2010, some of you may remember that a volcano blew up in Iceland, and that caused a massive disruption to air traffic around the world for a couple of months. The volcano was in the south of Iceland, and I was really lucky. I was in China, but I managed to get out to Iceland and make a documentary about the volcano. And that's me there flying over in a helicopter, and that's a volcano erupting. It was quite risky actually to fly that close to the volcano, but you can see the smoke and ash coming out of the top there. Hopefully my pen will work. Yep, so there's the smoke and ash coming out into the atmosphere. And that was the cause of all of the air traffic shutdown, which had significant economic impact. Right? So volcanoes, even if they explode and erupt a long, long way from where you live, the chances are they can impact on your life. So that's why they're a global phenomena. And it's important to understand their role in the place and in the way that they form on Earth. All right, here's a map that some of you may have seen if you've done geography or geology so far. It's the Earth minus the oceans, and the blue bits are the ocean basins, and the continents are the various colors. There's the reds and the greens and the yellows. You can work out, you can see North America, South America. Where I've just showed that picture from Iceland is up here. Right, that's Iceland, and each of these red dots on this chart, on this map, are where there's been a volcano and where there's been an earthquake. And there's a clear correlation around the world now, we understand, between volcanic eruption and earthquake activity. And in fact, the distribution of these dots define the Earth's plates. The Earth split up tectonically into about 12 plates. You've probably heard of plate tectonics. And the boundaries or the margins of these plates are defined and made out by these dots, which are volcanoes and earthquakes. So Iceland's up here. That's one of the most volcanically active places in the world. Lots of volcanoes going on there all the time. An interesting fact, perhaps, is that under the sea, where you join these dots up, that is the boundary between two of the Earth's plates. This is what's called the Mid-Atlantic Ridge. Most of the volcanic activity on Earth takes place under the sea, under 3 or 4 kilometers of water, pretty much out of sight and out of mind. It's only those volcanoes that blow up on land. As human beings, we live on the land, that's when they impact us significantly. Out here, I'll talk about that in a minute. That dot there, that's Hawaii, out in the Pacific Ocean. This massive cluster here is around New Zealand, loads of volcanoes in New Zealand. We'll talk about that in a second, not loads, number of volcanoes. This area here around the Pacific is called the Ring of Fire. You've probably heard of that, the Ring of Fire. In particular, there's an area around South America that I've done a lot of work in. This is the Andes Mountains, lots of volcanoes there. And this ring of dots forms one of the plates of the Earth, the Nazca Plate. The Nazca Plate has been subducted or sinking down beneath the continental plate of South America, causing volcanoes and causing earthquakes. So we've got a very good idea now of why volcanoes occur on the Earth in terms of place. What we also need to understand, and we're getting better at, is the different volcanoes erupt different types of lava, and the composition of the lava that comes from a volcano as it erupts will determine the style of eruption, and that's controlled by the chemistry of the lava, but also a key physical property called its viscosity, and I'll talk about that again in a second. Now, in terms of people, volcanoes have been frightening people since they've been around, I guess, since human beings first evolved. There's a picture, kind of a classical description, if you like, of a volcanic eruption taking place. People running, they're hiding, the buildings are falling over, there's fire in the sky. To be caught up in a significant volcanic eruption is a life-threatening event. I've not been caught up in one personally, but as you saw from the helicopter, I've come pretty close to exploding volcanoes. They've taken their toll over the years. Hundreds of thousands of people have died from volcanic eruptions. So it's important to understand, in terms of a human perspective, how we mitigate these risks, how we save lives. And that's an interesting part of volcanology in terms of hazards that's becoming more and more interesting to students and to researchers, because it's got clear public health implications. So focusing on place and a bit now on people, here's two nice photographs, pictures of volcanoes. This is Hawaii, right? Now this picture here is what people tend to think of as volcanoes, rightly so too. These hot rivers of lava flowing down from the summit here, the top of the volcano. The smoke here, by the way, is not from the lava, that's fire. So because the lava's hot, you catch fire to vegetation. So fire is a secondary hazard from the volcanic eruption. And the reason the lava is flowing down like this is because it's flowing down the slope of the volcano, right? So it's flowing down under gravity, right? Gravity is taking the volcanic flow, just like water flows down a hill, so the lava does out of the volcano. And knowing that, we can actually start to develop a very small, if you like, mathematical model that allows us to say something about how fast the volcanic lava will move down the hill. So it's driven by gravity. An important aspect is the angle of the slope. We'll call that theta. So imagine that there's a volcanic lava running down this hill like this in that direction. We need to know a few more things about it. We need to know what the density of the lava is, the magma. We call that rho. We can say something about how sticky the lava is. That's the viscosity. That's got this funny symbol eta. Excuse my poor handwriting. We also need to know something about the thickness, the dimension, the length scale of the flow. So we can call that T. If you put all those together, you can come up with a small equation that allows us to work out how fast the lava moves down the slope. Now, the lava itself isn't really a significant hazard to people, because you can see it's channelized and it tends to remain in channels, and as long as you don't fall in it or something, then you're not going to get injured necessarily by the lava. But Hawaii is an interesting volcanic island, because look at this picture here. This is Hawaii, right? So this is the lava that you're looking at there in the picture on my left. Is kind of flowing down from the summit like this. But most of the islands of Hawaii, and I say the islands of Hawaii, are all under the sea. And that's where the largest volume is, right? So that's a bit above the land in grey. They're what we human beings call the islands. So under the sea, there's a vast mass of volcanic material that's all connected up. So it produces a big structure, these volcanic eruptions over time. And what I'm going to talk about now very briefly, which is an interesting aspect of volcanology, are these scars. And look, there's one there around the side of the island. What these represent are landslides. All right, so the bigger hazard actually to people living above land is not necessarily the lava flow itself. It's if the volcano collapses because of a landslide. And you can see this, this is based on geophysical seismic images. All these big lumps on the sea floor on the Pacific Ocean are all bits of Hawaii that have broken off and flown as landslides under the water. Now that's a significant hazard because if a large enough chunk slips under the sea, that can cause a tsunami. So we now have a link between volcanic structures, big volcanic islands growing up in the sea, collapsing through periodic landslides to produce another type of hazard, which is a tsunami. And so if you're interested in this kind of volcanology, that takes you very closely, excuse me, into engineering. Because what engineering and engineers are worried about is particularly civil engineers and geological engineers are slope stability and landslides. So just a little bit about that. This is some work that we did a few years ago, a PhD student of mine, where we tried to model the, using maths and computing, the distribution of landslide deposits from a volcano, right? So down here, the map is a little volcano, it's collapsed, part of it slipped off, and you've had a landslide. Material, we call it the run-out length. This black stuff here is black material, is what's left behind. It's moved off in a direction. But if you look in more detail, we can start to pick up some of the structures that might be formed inside these volcanic debris or avalanche deposits, right? So look at this, you can see the different colors. There's a fault in there, there's a fault there, it's a rotational fault. So you produce these sort of blocky type structures, and all of that is really linking in field observations with geology and with engineering, with computing. So again, that's another area of research interest. And of course, this has really impact, because if your house was down here somewhere, right, living by the volcano, then you'd want to know, wouldn't you, what the impact of a big landslide would be. And also, in particular, could we predict when a landslide would occur because of the volcanic activity or because of other effects, climatic effects perhaps. Another area that plays some people interacting with volcanoes is through tourism. So you might be interested in business management, for example. Well, guess what? There's a tourist angle to volcanoes. Many of these volcanic structures are located in interesting, exciting parts of the world. There's sunshine, there's beaches, there's sand. And so they attract people, and why not? They're exciting places to visit, but they can be incredibly dangerous. Now, this is a photograph taken in December 2019, just less than a year ago. It's White Island. You might remember seeing that on the news. There were people who got a boat out from New Zealand, from the mainland, visited the volcano. There was a small eruption. About 21 people were killed, and maybe as many others injured. Made the news headlines. So although there's a link between tourism and volcanoes, they're dangerous, you know, and there's an interesting aspect here as to how volcanology can work with local tourism industries, with economics, you know, even with perhaps the psychology on how do you visit volcanoes, how do you visit them safely, you know, because the volcanoes themselves are tourists hotspots. They make money for local people. You can't stop, you can't regulate necessarily, but you want to do it as safely as possible. So here's an example: the poor people who are injured and killed that have landed by boat and perhaps walked across. There was a small eruption. In terms of a risk management piece, well, what about if they came up this way and stood on the top? You know, they might have been perhaps protected by some degree from the volcano. So this is just sorts of ideas that are growing, attracting more interest in the geological community, linking volcanoes, tourism, and safety all together, because you can't stop people visiting volcanoes, but let's make them as safe as absolutely possible. So that's an interesting area as well. In terms of safety, well, how do you monitor volcanoes? Well, there's lots of ways. There's land-based. Okay, so here's somebody using a spectrometer to look at the gas. This hazy stuff here is volcanic gases. What are they? Well, they're carbon dioxide, sulfur dioxide in there, and some water, H2O. And this machine here can analyze the composition of the gases coming out of the volcano. And if the gas compositions change quickly, that might tell you something about a potential eruption. It might mean that the magma beneath the volcano is changing. So it will alert us to that. Seismometers, geophysics, right? These are an array of these are 4 seismometers on the island of Montserrat. And I'll draw for you. Normally there's a nice, a nice normal trace if there's nothing particularly happening. If there's tiny earthquakes under the volcano, and what that means is that's a signal that magma might be moving beneath the volcano. If it is, it could be then on the way to erupt. So you'd expect to see something like that, ziggy zaggy, all of these things. If you pick up these signals, actually there's earthquakes. Again, that's the way to measure and assess the likelihood of a volcanic eruption. Another way is actually to use satellites from space. So the final one, let's say, is the volcano down in Italy there. The satellite's monitoring what's it looking at. It's using GPS. This is a very advanced GPS station. Can look at slight movements or tilts around volcanoes on the millimeter scale. It's a military grade material, military grade kit. So a combination of seismics, gas spectrometry, and GPS can allow scientists, earth scientists, to monitor volcanoes really, really carefully. So there is an industry in this, and there are job opportunities for you should you wish to study volcanology or geology and go on to work in the area of volcanic monitoring. Volcanoes also produce very powerful explosions that can affect the Earth's climate. So if you're interested in climate change and global warming, then volcanoes have a place to play there as well. This is a series of slides from the eruption of Mount Pinatubo in 1991. That's June the 16th up to June the 25th. And what we're looking at here, so Mount Pinatubo is in the Philippines. Down here, this is the equator. Oops, no, that's not, that's somewhere else. Sorry, guys. This is the equator here, the poles, obviously. This color chart here, that's where the eruption was. What we're looking at is a scale here between the blue color, which is marked 10, and the red color, which is marked 1,000. This is the amount of sulfur dioxide, SO2, in the atmosphere following volcanic eruption over the period of a couple of weeks. And what you can see if you go from the slides from here, that the plume, the volcanic plume, is up in the Earth's stratosphere now, out of the way of rain. So it will stay there for a couple of years at least. And it's moving around the entire world. And the sulfur dioxide, about 20 million tons of SO2 was erupted up into the stratosphere in 1991. And over a couple of years, from 91 to 93, it cooled the Earth by about 0.5 degree centigrade. So what we're looking at here actually is an interesting way to cool down the Earth through volcanic eruptions. So who knows, in the future, perhaps there'll be some kind of geoengineering sorts of projects where you could inject sulfur dioxide into the Earth's atmosphere and help to cool down the planet Earth as it heats up. That's another area of interest. This is all from the Nimbus 7 Tom satellite that gathered these data. Coming towards the end now, what about people who live close to volcanoes? There's often been a focus in the past just on the science of volcanoes and volcanology, but we're talking about real lives. You know, every year people are displaced by volcanoes and killed. What's their story? This is a picture of the capital of Plymouth in Montserrat, which has been pretty much destroyed by volcanic activity. All the stuff you can see in the foreground, these big blocks of debris flows, mud flows, landslide material, with perhaps some pyroclastic material that's come down from the volcano, which is out of shot. And that's a local store. There's a supermarket, there are houses. Everybody had to be evacuated from this. How do you do that safely? You know, how do you sensitively remove or evacuate people into areas of safety who perhaps don't want to go? So this takes on a new slant from volcanology, looking at the volcanoes and then thinking about how people respond to them. So there's some psychology in here, there's perhaps some sociology, and also the cultural traditions of people who have been affected by volcanoes. What's their story? And there are stories. There's a great cultural history of people from around the world who've lived on the slopes of volcanoes, who perhaps know a bit more about it than some of the scientists who come in from the West. You know, these aren't our countries, we're guests out here, so we should be very sensitive to the and responsive to local people when we go and work with them in partnership in order to make their lives safer. So that's another area of volcanic activity and research that's becoming increasingly important. The area that I work on mostly, and again, this is very close to the end of the presentation now, is looking at, if you like, mathematical models or models of how the lava, the magma, moves beneath the volcano. Now, if I were to ask you what this picture is, where in the world this is, you might think, well, it's very barren, it's very dry, I don't know, some kind of desert perhaps. Well, let me tell you, this is Antarctica. This is the dry valleys in Antarctica, big mountains up to several kilometers high at least. and it hasn't rained here for thousands of years. It's incredible. There's no vegetation either. So that means if you're a geologist, you can see the bare rock in the best possible circumstances. What we're looking at here is a feature which in geologists call a sill, right? I'm interested in this darker structure here. I'm going to highlight it there. There's one there, there's one up here as well. But there's 3 or 4 of these layered sills that about 170 million years ago in Jurassic times were full of liquid lava. And the lava was moving, the magma was moving horizontally. And we think this is a great example of what it might be like, maybe 3 or 4 kilometers beneath Hawaii now, the Hawaiian volcano. Clearly we can't go down. There's no sort of magma, there's no rock submarine that allows us to go inside the earth. But what we can do is look around the planet for places where the volcanic edifice has been removed and eroded away, and you're left behind with the plumbing system. We call it the plumbing system. What might have been like behind it, what the volcanic plumbing system might have looked like. Of course, there's no longer any liquid here. It's all turned to rock. But we were interested in what the lava, what the magma was doing beneath the volcano, how it was moving around in Jurassic times, you know, hundreds of millions of years ago. And the only way we can really do that is through some kind of computer model. This is the kind of stuff I tend to get involved with more these days. A numerical model, and if you're interested in the physics of volcanoes or physics in general, combined with engineering and fluid flow, then again, there's another area of interest for you in volcanoes. Okay, what we've done simply here is use a mathematical model. This is called the Navier-Stokes equation. That's the viscosity of the magma. Spoke about that earlier. That's the density of it. That's the pressure change. 3 coupled terms with an external force taking place here. This is for an incompressible fluid. And we solved that, the Navier-Stokes equations in this mesh here. Every time, you can see that mesh quite clearly. I hope you can see it looks a bit funny. Every time there's an intersection there, that's where this equation is solved. It allows us to build up a numerical model, which is this, the colorful picture. And what it's showing is the magma, what the magma might have looked like 170 million years ago, flowing laterally through this pipe. So that's an interesting area of volcanology. What that allows us to do is to build up a picture of the plumbing system beneath the volcano and how the eruptions, what might subsequently follow on from this type of modeling. Finally, out to space, right? The last area I'm interested in is extraterrestrial volcanoes, ET volcanoes, if you like. This is a photograph of the moon Io, which is one of the 4 large moons around Jupiter. This was taken in 1979 by Voyager 1, a spaceship, which is still out there actually, still sending data back way on the edge of the solar system now. This thing here, you might miss it at first glance. It's the first ever photograph of a volcano erupting outside the Earth on the planet Io. The plume here is about 200 kilometers high above the surface, and it's an extraordinary picture. And since then, we've discovered that Io is one of the most volcanically active places in the entire solar system. Nearly everything you can see on this picture, the colors, the dark bits here, the lighter bits, are volcanic or volcanic related features. So that is of interest. What I think is absolutely mind-blowing to me is what we see right out of the farthest edges. Right, this is my last slide. This was taken in 2015, series of photographs by the Pluto Express, traveling out to Pluto and beyond. As it flew past, this is a photograph near towards the south pole of Pluto. The box area here is of extreme interest. Okay, this is an enlargement of it. What we think this structure here might be is a volcano, right? But what kind of volcano could that be on, well, it's downgraded from a planet. Let's call Pluto a planet anyway. Out there, millions of miles away from the sun, with a surface temperature of -200 degrees centigrade. What kind of lava would come out of a volcano like that? Well, it appears that the kind of lava is ice or ice ammonia mixtures. So we call these sorts of volcanoes cryovolcanoes, right? And it might well be that a lot of the activity out in the outer solar system, a lot of the volcanoes aren't hot at all, like on Io. They're actually cold. So cryovolcanism. Clearly no human being has been there yet, but perhaps one day somebody will launch a field trip to Pluto and they'll climb up to the top. It's about 4 kilometers high, that structure actually. It doesn't look like it from here. It's got a name, it's called Wright Mons volcano, cryovolcano, question mark. So I'll end there. Lots of exciting opportunities. So if you're interested in astronomy and physics, then the link there to extraterrestrial volcanoes might be of interest to you and some excitement. So I'd recommend the study of geology, the study of volcanoes. I hope that's been useful. I'll stop there and ask and open up the questions. Thank you.